So this is part 2 of glycolysis, and in the previous video we answered some questions about glycolysis, right? In previous video, the part 1, we discussed why does glycolysis even exist and what is glycolysis trying to do, in this video, what we're going to do, we're going to understand the exact function of these glucose molecule, right? Why, what's happening? It's the continuation of part 1. So if you have not seen the part 1, I would really suggest you to watch the part 1, right? Now let's close your eyes, and I want you to imagine that again you are the cell. Someone gives you one glucose molecule. Now the question here is that what do you actually want from the glucose molecule? Do you want the glucose molecule itself, or do you want ATP, NADH, and pyruvate? These three things. You want ATP, NADH, and pyruvate. Pyruvate for the further metabolism, right? Glucose here is the raw material. It's like someone gives you maybe some $100 bill. You walk into a vending machine. The machine only accepts $10 bills, right? Now the question here is, can you use the $100 bill directly? No. First, you must break down this big glucose molecule into smaller units. Cell do exactly same thing. Okay, cell do exactly this. So let's go to the part 2. Let's understand what is happening here. Okay, so glucose, right? Glucose has glucose has 6 carbon molecules, okay? 6 carbons, right? And cell eventually splits this into 2 packets. 3 carbon packet and a 3 carbon packet, okay? So we have 3 carbon molecules. Everything after the split happens twice in the whole reaction, okay? So this explains why we have this 2 ATP and 2 NADH as the results, okay? So this phase right there is the split. I want to call this split so that we will remember this. This is the split. And after this we get 2 because we are having the reaction in 2 different directions, right? Not different, 2 directions simply, right? So first question is, why the split, right? Why not keep glucose intact? Because extracting energy from this large molecule all at once would be super duper tough, and it will be super duper wasteful. So nature prefers small, controlled, and this enzyme catalyzed steps, right? Think about cutting a tree. You don't explode it, right? You cut it piece by piece. So that's the same way nature does it. So the overall glycolysis is, let's just ignore the whole enzyme buildup for a moment. Overall reaction is that glucose, you get 6 glucose, right? That's glucose. You split it into 3 carbons, and then eventually you get 2 pyruvate, 2 ATP, 2 NADH, and 2 H2O, right? So eventually from glucose you get 2 pyruvate, 2 ATP, okay, 2 NADH, and 2 H2O. So this is the result of overall glycolysis, right? Notice something. 1 glucose becomes 2 pyruvate, right? So 1 glucose is becoming 2 pyruvate, right? Why? Because glucose has 6 carbons. So pyruvate has 3 carbons, okay? So this is conservation of mass right there. Conservation of matter right there. 1 pyruvate molecule is equals to 3 carbons. So as you can see, we split the glucose and then we have 3 carbon and 3 carbon right there, right? So that is we call as conservation of matter, right? Nothing disappears. Now where did the carbon exactly go, right? I mean, let's count it. We have 6 carbon right there, right? After the split, we have 3 carbons, that's one pyruvate. And then other 3 carbon, that's another pyruvate, right? So every carbon is accounted for, right? So it's only we are just rearranging them, right? That's the split right there. Now, what does glycolysis produces, right? We trying to understand. We trying to understand. Now we know that it produces ATP and ADH pyruvate, like, right? But we want to understand what exactly is their function, right? So first of all, let's ask about ATP. In the last video, I already introduced you to the ATP. Once again, I'm going to tell you, ATP is immediate usable energy. It is used by muscles. Okay, used by muscles, used by ion pumps, right? Used by signaling molecules, used in signaling, I should say. Signaling, right? What about NADH? Well, NADH is super duper amazing. Why? First of all, what is NADH? For now, I want you to think NADH as a taxi or as a rechargeable electron battery. So it's a battery, right? It's a cell. It's rechargeable. We'll study it deeply later on in the next parts. But for now, remember, ATP carries the energy for immediate work, and NADH carries the high energy electrons to be used later on, especially in mitochondria. Okay? So that's your mitochondria right there. What about this pyruvate then? Well, your pyruvate. Is pyruvate wasteful? Absolutely not. Pyruvate is like a crossroad, okay? It is a crossroad. It depends upon oxygen now. It may become acetyl-CoA, can become lactate, can become oxaloacetate, can become alanine as well. So glycolysis is the beginning and pyruvate is the crossroad of other pathways. So it's a crossroad. It's the decision you take. Which way should I go? Depends upon aerobic or anaerobic. Hypoxic, not hypoxic, right? So pyruvate is the crossroad, right? Okay. So let me introduce you to phases of glycolysis. The whole glycolysis can be broken down into 2 phases. Okay, so I'm going to put 2 phases here. What am I even talking about, right? I'm going to answer you all the questions. Just listen to my story. The story is that we have 2 phases in glycolysis. This is one of the very important parts of this whole glycolysis, right? Now, we ask ourselves, why do we spend ATP before making ATP? Right? This is an excellent question. This question actually explains the entire pathway. So we have 2 phases of glycolysis. Let's start in phase 1. This is phase 1. In phase 1, right, we are investing the energy. So we put the energy in. So this is investment. We are putting the energy in. The cell spends this ATP. Why are we spending? Because we want to split the carbon atom, right? So imagine pushing a heavy car uphill, right? You spend the energy first, then the car rolls downhill. So this, when we push the energy in, when we invest the energy, we call this phase, or we call this, phenomenon as activation. So this is called activation phase, or activation simply. So this is activation. The cell activates the glucose. We are pushing the energy in. This is phase 1. Okay, the cell is activation of what? Of glucose. So ATP investment, right? Let's talk about ATP investment. The cell cell needs around 2 ATP. How much? 2 ATP. 2 Cell needs around 2 ATP before earning anything. Many people think that this is stupid, but actually it's amazing, because activating the glucose actually makes the glucose chemically reactive, right? Chemically reactive enough for later energy extraction. So how much energy we put in? We put in 2 ATP. Now let's go to phase 2. So this is phase 2. Now we are in phase 2. This phase is the energy payoff phase. We get the energy back. We are getting it back now. Payoff, right? So that's payoff phase. Now the activated intermediates releases this energy, right? The cell captures the energy as what? As ATP and NADH. The investment has recovered and the profit has happened, right? So the investment was initially 2 ATP, right? Later in the phase 2, we earn about 4 ATP. Okay, so the net profit is around 2 ATP. That's the profit right there. Exactly like investing money in real life, right? So now you can ask me, well, Shashwat, why the profit is about 2 ATP? Let's calculate from the beginning again. In the beginning, we spent around 2 ATP, right? Let's start with the beginning. We spent ATP to get ADP, okay? As you know, right? Here's the thing. ATP is broken down into ADP and inorganic phosphate, right? And this is hydrolysis reaction, right? This happens, the cell does it, okay? So we get ATP and we get ADP and inorganic phosphate. Note that after the split, we have these reactions happening simultaneously 2 times, right? One in this way, one in this way. So here we get ADP plus inorganic phosphate, and there as well we get ADP and inorganic phosphate. So we get ADP twice. So that is minus 2 ATP, because we put 1 ATP here and we put 1 ATP here. So that's minus 2 ATP, right? So let me go to the phase 2, right? From the beginning, we put 2 ATP, right? So minus 2 ATP first. Okay, simple. Later, this ADP is transferred or converted into ATP twice. Again, here, because we have 2 rows, right? So this ADP gives us ATP, right? And it happens twice because this is another column, right? So we are getting 2 ATPs, okay? But remember, everything happens twice after the glucose splits. So therefore, we get 2 ATP. 1 ATP from this row, from this column, and 1 ATP from this column, right? I hope you know that. I hope you understand this, right? We're getting 2 ATP now again. So, nice. So now we got, so in phase 2, first we invested 2 ATP. Now we got the 2 ATP back, right? So everything happens twice, therefore, right, we get 2 ATP. Now the cool thing here is that we just don't get 1 ATP in one column. We actually get 2 ATP. So 2 ATP from one column and 2 ATP from one column, right? So that's how it is. So eventually we recover our loss and we get an extra 2 ATP as well. So that's a profit right there. So net profit is 4 and we spent around 2, and net is 2 ATP, right? So we are in a profit of 2 ATP. Okay, so I explained to you why we have 2 ATP. Now you can ask me, why everything happens twice? Well, this is the split. Again, let's look at the split. This is the split right there. Before splitting, we had 1 glucose molecule, that is C6, right? 6 carbon molecule. 1 glucose, 1 molecule, every reaction occurs once, right? After splitting, we have these 3 carbon molecules, right? We have these 3 what? We have these 2 glyceraldehyde 3 phosphate molecules. What? 2, we have these glyceraldehyde 3 phosphate molecule, right? Now every downstream reaction happened twice here, right? Because we have two streams simply. Okay, we have this is one stream, the upstream, this is the downstream, okay? Okay, so we have this glyceraldehyde 3 phosphate, and we here also we have. This is the reason why we get 2 NADH, 4 ATP, right? 2 ATP in every, so we get 4 ATP, right? 2 NADH, 4 ATP, and 2 pyruvate eventually. But because enzyme become faster, because there are two substrates now, because not because enzymes are faster, okay? Want to put this idea in your brain. All this is happening not because of enzyme. This is happening because we have two substrates, because we have this substrate and this substrate, right? This is the big deal, right? So why doesn't glucose split immediately, right? You can think about it. Because glucose is very stable right now. First, the cell changes it, right? Let's talk about it. Why glucose doesn't split immediately? Why? Well, glucose is super duper stable, right? 6 glucose, these are very stable. Cell changes it. How cell changes it? Cell needs to change it. How will it change? Cell will put what? Cell will put a phosphate, right? Now the thing with phosphate is that phosphate is PO4 negative. Now this negative actually means that it has one electron that is free, or it's charged, I can say that, right? Now once you add this phosphate to maybe anything, honestly, you can add it on a glucose, you can add it on, I don't know, something else. But once you add the phosphate on something, you actually make it polar. Once you make it charged, it cannot cross the cell membrane. So the concept here, what I'm trying to say is that to make sure that glucose doesn't leak out of the cell, we need to add a phosphate to the glucose, right? This is called phosphorylation, right? So because glucose is super duper stable, the cell needs to modify it and adds a phosphate, right? Only then it can split it efficiently. Every modification prepares it for the next step, okay? So this is very important, right? Why are we adding phosphate? Because phosphate group increases, first of all, reactivity, traps the molecule inside the cell, stores this energy, and creates these recognition sites for the enzymes. So adding a phosphate gives us two things. First, traps the glucose. Second, what it does is actually it creates a recognition site. The cell can now recognize, the enzymes can now recognize. Think of phosphate as putting a handle on a suitcase. Now enzyme can actually grab it, okay? So that's the thing. Now, why doesn't the glucose leave the cell immediately, right? Because free glucose, as we know, is super duper water soluble, right? So free glucose can cross transporters. But once they are phosphorylated, right? Once they are phosphorylate, wow, I love this word, phosphorylated, right? Once you change the glucose, okay, let me write, glucose, we phosphorylate here, we add a phosphate, what happens? Glucose becomes what? Glucose becomes glucose 6 phosphate, because we add the phosphate at 6 position, right? So glucose 6 phosphate. Simple. It carries this negatively charged phosphate. Now charged molecule cannot easily cross the lipid membrane, so therefore phosphorylation traps the whole glucose, right? And we can call this whole thing as what? We can call this thing as metabolic trapping. Metabolic trapping. That is your metabolic trapping happening right there in front of you, right? Now we'll study about this metabolic trapping more when we'll study something which is called as hexokinase. In this video, we'll focus on glyco on the reaction itself. Okay. So hexokinase. We'll come back to it. Don't worry. Now let's come back to the NADH itself. Why NADH? Right? Why are we producing this taxi or battery? Why NADH? Why? Why not produce just ATP? Because ATP cannot carry these huge, large numbers of electrons. Okay, so NADH is a big taxi. Remember this, right? So remember, glucose contains these just big energy, big chemical energy. Some of the energy can be stored as ATP. The rest of it has to be stored as NADH. Later, what happens is that NADH donates electrons to the electron transport chain, right, in the mitochondria. So big taxi for electron, right? ATP is the cash, the immediate cash. NADH is the money that is deposited in your bank, right? Now, what about oxygen? Notice something. There is no oxygen, right? So oxygen does not appear anywhere in the glycolysis. So let me write this here. No oxygen needed. That is the reason glycolysis can continue in exercises, in hypoxic situations, and in RBCs, right? However, what happens is after glycolysis happens, it depends heavily on oxygen. What will happen? Okay, the crossroad, the pyruvate crossroad, right? Let me make it. So the pyruvate crossroad depends upon aerobic or anaerobic. So oxygen depends upon oxygen here, if we have oxygen or not, right? So here, I have always one rule. Whenever I am thinking about some concept, I want to think, when will this concept actually fail? So when does glycolysis fail? Ask yourself, what if glucose cannot be phosphorylated, right? Glycolysis will stop immediately because you will not have any glucose to lysis, to break down, right? Why? Because glucose cannot be trapped inside the cell or be activated for further metabolism. If you don't add the phosphate group, you will not create a recognition site, or you will not trap the glucose, right? That's one thing. How can the glycolysis fail? Even more, in what ways it can fail more? What if the ATP is unavailable? So what if ATP is not there at the beginning, at the phase 1, right? What if ATP, we don't have any ATP right there at this moment? If we don't have ATP at this moment, there will be no splitting, there will be no activation, no phase 2 as well, right? So there will be no phase 2. And because the phase 1 depends upon the investment of the energy, right? So we need to put 2 ATPs first. So that's important. You need ATP to make ATP. You need money to make money, right? So cell always try to maintain a small ATP reserve to initiate this pathway like glycolysis, right? Okay, what about this pyruvate kinase deficiency here? You told me that, Shashwat, you told me if we have pyruvate kinase deficiency, we're going to have hemolysis. Let's understand it a little better, right? So pyruvate kinase deficiency is dangerous. Why? Why is it dangerous? Why is it gonna kill you? Because RBC depends upon glycolysis entirely. If final ATP producing step is impaired, that is the pyruvate kinase step, right? We will have less ATP. If we will have less ATP, remember these pumps. I told you what the cell has to do. Na out and potassium in, right? So we have these pumps right there. What pumps? Na, sodium, potassium, ATPase. ATPase means it uses ATP as a source, as a fuel, right? What will happen here is these pumps will fail. Once they will fail, what's going to happen is that the cell membrane is going to become fragile. If the membrane becomes fragile, we're gonna have hemolysis, right? Note that the disease is not primarily about pyruvate, it's about ATP deficiency. So this is happening because of ATP going, low. Other diseases can also mimic the same result, right? So hemolysis, this kind of hemolysis can happen in other conditions as well. This is important. Now there's a very famous question in I don't know in a lot of platforms that energy drinks increases glycolysis, right? Energy drinks increases glycolysis. Now this is famous, super duper famous question. Energy drink increases the activity of which irreversible enzyme? Think about it. Energy drink has what? Energy drink has, first of all, glucose. First thing. Second, what does it has? It has sucrose, also sugar. Third, what it has is caffeine. Often, most of the time, right? Caffeine. So it has these three things, right? Now you are actually loading yourself with so much glucose, right? So glucose load increases what? It's gonna increase glycolytic flux in insulin responsive tissues, right? What am I even saying? Okay, why? Because as more substrate enters into glycolysis, right? This is glycolysis. If we have more glucose, right, the pathway irreversible control points must process that increased flux, right? So pyruvate kinase, right? Pyruvate kinase, this enzyme, right? The pyruvate kinase, which catalyzes, means fasten, increase the speed, right? It catalyzes the final irreversible step. Therefore, drinking more gorilla or energy drink, right? Therefore, it shows increased activity of glycolytic throughout glycolytic process. Later, we will discuss how the hormone and allosteric regulators modulate this whole thing in detail, right? Because we are basically increases the glucose input. And which enzyme will increase? Pyruvate kinase, because this is the last irreversible step enzyme, right? So that's the second part of this video. In this part, we discussed phases, phase 1, phase 2. We discussed that glycolysis has an investment phase, right? Followed by a payoff phase, phase 1, phase 2. We need to produce 2 ATP is consumed. That's the investment. We get 4 ATP, right? 2 ATP in each stream, right? Net gain of 2 ATP. 1 glucose yields 2 pyruvate because glucose contains 6 carbons and pyruvate contains 3 carbons, so 2 pyruvate. After glucose splits into 2 3 carbon molecules, every downstream reaction occurs twice. Okay, that's also true. And glycolysis occurs entirely in the cytosol. It is very important and does not mess or need oxygen. Okay, so if the question asks you 2 ATP, 2 NADH, 2 pyruvate, anything like that, we want to think about glycolysis. Okay, so that was your second part of the video. Now the concept to understand and remember here is that we understood investment, we understood split, we understood energy, extraction of energy into ATP and NADH. We understand what the hell is going to happen with pyruvate and NADH and ATP, right? And we understood that glycolysis produces pyruvate, right? We understood. Now, this was your part 2 of the video. So I'm going to upload this and we will meet in the third part. It's better to produce these multiple parts rather than talking continuously because I get super duper tired of speaking. So that was part 1. This is part 2. Let's talk about part 3. In part 3, we are gonna talk about these irreversible versus reversible steps. Okay, so irreversible steps one by one, starting with hexokinase versus glucokinase, right? Explaining why glucose must be phosphorylated first, because I already explained it, but I'll explain it again so that you understand the hexokinase, glucokinase, right? And what else? What else? We can okay, so that's so basically we'll try to understand the irregular steps, right? This reaction, this 1, 3, and 10 are irreversible. Why? Okay, so we'll understand this in the part 3. Okay guys, have a nice day. That's a 30-minute video. Nice.